Hello? First, I want to thank the organizing committee and particularly Ali for inviting me, and this is a very fascinating meeting. And we're going to talk a little bit on magnetism today, and we're going to, can everybody hear and back? There's action over there. So we're going to talk about magnets based on organic chemistry, or spins in p orbitals to do that. And I'm assuming the audience is mostly physicists, and I'm a chemist, so you may have some questions to raise as we go forward. Appreciate if you would not photograph some of my slides. I've taken them in strange places, and I don't want to have them appear up in other places. First, let's do a little introduction, as previous speakers have done, about the topics of the day. And that's the history of magnetic materials. And this has been incredibly important for the development of our civilization. Magnetite, Fe3O4, lodestone, basically has been around forever, but it was Chinese people who discovered its magnetic properties and did something that I think we talk about in this conference, is technology transfer, of taking an important scientific discovery and convert it into a commercially valuable product. And in this case, it was making a simple compass, and it did not turn out to be financially successful because they did not invent the cash register at the time. But if they had, there would have been lots of money to be made. So that's the beginning of technology transfer. And the word magnet actually comes from a shepherd Magnus who was wandering around actually this part of the planet. It's unclear to me that people know exactly where he was. Some people think he is in current Greece, and other people think is in current areas of Turkey, and we are down over here, so we're fairly close to the actual discovery of magnets that were basically rocks adhering to the shepherd's shoes. So that's the ancient history of magnetism, particularly as it's attributed to this area. And this, of course, was important for the discovery by Christopher Columbus of what they called the New World at that time. But scientifically, a key discovery was made by Petrus de Maricourt in 1269. I would argue he was the first experimental physicist around. He proved and disproved theories. He improved the compass by putting it on a pinhead so it could spin. He invented or identified the north and south magnetic poles. And he answered the question every kid answers, is that if I have a magnet and break it, do I have a broken magnet? And the answer is you get two smaller magnets out of it. And so we all know that, but the first person to do that, and he wrote it down in Latin in 1269, and so he was the first published, and I think he did perish at that time. Going forward, William Gilbert, who was claimed by Galileo to be the first experimentalist, he was a synthetic chemist. He made the first natural occurring magnet, iron metal. He wrote this all down in a fairly thick book called The Day Magnet in 1600. And importantly, being a physician, he actually debunked many myths and superstitions about magnet. But crucially for us, and if you think about the fancy experiments we talk about today, and we take advantage of that because of newer, better experiments lets us push the boundaries of science, he actually identified the earth as a magnet. And this actually is a very interesting thought process. If you think about the scientific equipment he had in 1600, he actually had no computers. Abacus wasn't invented. So the basic computing skills was limited to the volume between his ears and the compass. And from that, he actually deduced that the Earth itself was a magnet, which has not been debunked. Hans Christian Ørsted showed that electricity affected magnets. Michael Faraday invented the first electromagnet, and subsequently in the Niagara region of northwest New York State, low-cost electricity became available in 1886, and the world has been electrified since then. So magnets are very important, but all that time, no one understood why. Just understood it was magnetism, and it wasn't until quantum mechanics and Niels Bohr realized that, in fact, it's a quantum phenomenon. So that's the quick history, cherry-picked, of magnetism that we have. And today we're going to talk about magnets based on organic chemistry. And we're going to define them as magnetically ordered materials. Ferro, ferri, or antiferromagnetic with a magnetic ordering temperature. They will possess unpaired electron spins residing in a p orbital that contributes to the magnetization and the magnetic coupling controlling the overall magnetic behavior. In other words, if you don't have the spin in the p orbital, it will not magnetically order for the materials I will talk about. And the materials you're familiar with are going to be metals, metal oxides typically, spins in d orbitals or f orbitals, but not in p orbitals. So we're going to branch magnetism into organic-based materials. And they're not paramagnets, they're magnetically ordered. Now the advantages of this is that you can use organic synthetic chemistry to develop materials, combine properties, change properties, and simplify the processing and fabrication. Magnets you're familiar with, iron, chromium dioxide, neodymium iron boride, are high temperature metallurgically prepared materials, and they're energy intensive. Organic-based magnets can be, in principle, insulating, transparent, biocompatible, and technically have high permeability. Now, the disadvantages, also by the way, an advantage is that there is an incentive, particularly in the United States or in the free world, to replace and improve upon rare earth materials with earth-abundant elements, because the important rare earth magnets, which are essential for computers and iPhones and who knows what else, are 97% produced in China and export restricted, so this is a limitation and concern in the future. Now the disadvantages, no one's ever made them, so no one's ever going to use them. They're going to be organic, low density, high equivalent weight. In other words, big molecular mass per spin, and generally low spin orbit coupling. But this actually may be advantages for spintronics and magnetics. In those emerging areas where magnetism plays a role, this actually may be a benefit to doing that. Energy values will be more free electron-like. Now the actual question is, philosophically, can you actually do this? We can dream about it, and there was a physicist who received the Nobel Prize in 1977, Phil Anderson, who was instrumental in using quantum mechanics for solid-state condensed matter physics. He thought about the problem, and he basically concluded it was improbable to make a magnet based on organic chemistry. So we're coming from behind the 8 ball and an unlikely position, but we're going to tell you how you can achieve magnetic ordering in organic-based systems. So the first reaction we did many years ago, excuse me, you asked me for permission for an equation in mathematics, I'm going to use equations in chemistry. No math equations for me. So decamethylferrocene, for the uninitiated, iron to low spin diamagnetic sandwiched between two 5-membered rings that have each 5 methyl groups on it, decamethylferrocene. It acts more like benzene than it does iron. And tetracyanoethylene dimethane used to make a lot of organic-based metals in many cases. We mix them together, and the iron 2 gets oxidized. Whoop. I hate to ask what happened. Over here to iron 3 low spin, and TCNQ picks up an electron, become a radical anion, and forms an alternating chain of alternating cation radicals and anion radicals. And we studied the magnetic properties of this material. Now, we were interested in it, to be honest with you, to make an organic conductor metal. That failed. But nonetheless, we got some interesting magnetic data. It's a little hard to see, and I apologize, but on the y-axis is magnetization, and the x-axis is Kelvin, 1 to 6 Kelvin. And when you look at the magnetic susceptibility, as you measure it at 1,000 Gauss applied field, it goes up, reaches a maximum, drops down. That's an indication of antiferromagnetic behavior, and not particularly a surprise. But if you do the same experiment at 2,000 Gauss applied field, it goes up, stays up, we take it down to 60 millikelvin, never comes down, and acts like a high moment ferromagnetic state. And ultimately, we studied this in painful detail and determined that it is a metamagnet that switches between the antiferromagnetic to the ferromagnetic state at a critical field of 1,300 Ersteds. So it's magnetically ordered, but with an antiferromagnetic ground state for this material. So we hypothesized that if we can take this benzene ring out of the TCNQ, you would make TCNE, tetracyanoethylene. It's like polyethylene, except instead of hydrogens on the carbon double bonds, it's got cyanide groups. And that's almost as easy to reduce as TCNQ, but it's half the size. So if it's half the size, that and the same number of spins, that means the spin density is twice, and therefore it's have stronger coupling. It's also smaller, so it can get closer to something else and have stronger spin coupling. And so we anticipated and hoped this, in fact, would lead to a ferromagnetic ground state instead of a antiferromagnetic metamagnetic ground state for this material. And so we proposed the synthesis of decamethylferrocene TCNE. We targeted it, we went in the lab, it was painful to make, I won't go through that. But the fact of the matter is it oxidizes the iron 2 to iron 3, it picks up a spin, the TCNE is reduced to the radical anion, picks up a spin, and in fact, we'll talk about the structure later, but in fact, I'm simply going to tell you at 4.8 Kelvin, it magnetically orders as a bulk three-dimensional ferromagnet for this material. And here is some data, we have a lot more data than this, for it. Hysteresis loops with a 1,000 Gauss coercive field. This is 2 Kelvin data for it. It is 37% more magnetic than iron metal is on a per iron or per mole basis for this material. And here is a pellet of it in a liquid helium dewar in a cobalt samarium magnet here. And you pour in liquid helium, it gets cold. When it gets cold, it goes below TC. When it goes below TC, it's highly magnetic, jumps up to the magnet, let the helium boil away, it gets warm and plops down. So this demonstrates that this molecular material, which is more ionic than sodium chloride, is a magnet. And in fact, it's the first organic-based magnet that TCNE has a spin on the p orbital. And we've done all the controlled experiments by replacing that. And if you don't have it there, the iron you will not get magnetic ordering. It's soluble, you can dissolve it up in many solvents, remove the solvent, it's still a magnet, and you don't need high temperature metallurgical processing to make it. The structure is alternating cations and anions, as I indicated earlier, more ionic than sodium chloride, as I just mentioned. For it, some computational analysis of it indicates the intra-chain coupling is ferromagnetic and a factor of 250 times greater than the interchain coupling for it. So it's mostly one-dimensional, which is a little bit of a problem from some people, but the fact of the matter is, of course, it is three-dimensional in its structure, and the observable as it does magnetically order for the material. So we did a little funny chemistry over here. We took the iron out and put vanadium in. We took the 5-membered ring out and put a 6-membered ring in. Bis, benzene, vanadium, plus TCNE, also in the same solvent, dichloromethane, gives us a material that has no benzene in it. And nowadays we make it from the vanadium carbonyl and TCNE. It's nominally the same structure. And if you mix it up in solution, we first saw black spots. Those black spots accumulated at the ends of the magnetic stirring bar, which is not rotating here. You can see it over here and here to doing that. And if you measure the magnetization versus temperature, you can, at low field, you can see that in fact there's a bifurcation, the field cooled and zero field cooled, and it goes to zero at 400 Kelvin. So the experimental ordering temperature is 127 degrees centigrade, 400 Kelvin. Now this material unfortunately has a thermal rearrangement around 360 Kelvin, which limits the observed critical temperature. And if you play physicist for a moment and use the Blocky law to do it, you can extrapolate based on the data on top here over to here that in fact magnetically orders at 645 degrees Kelvin, 372 degrees centigrade. We can't achieve that experimentally because of the disorder, but from intrinsic value, that's what this material exhibits. Just to show you, it's an amorphous material, by the way. It just doesn't diffract. It's pyrophoric, which means it catches fire in the air. And you can see that, in fact, just sticking a magnet on it, it can pick it up quite easily. So it's quite a robust magnetic material, but you have to keep it away from air. Of course, the rare earth magnets you have to keep away from air because they're hazardous too. We've learned how to make thin films by chemical vapor deposition. We have a simple system. We operate below 40 centigrade in here with argon stream and vanadium carbonyl going this way. Heating up a little bit more on the TCNE side. Vapors at TCNE, they both mix. Anything in the middle gets coated with the vanadium TCNE magnetic material. And you can see that over here, there's less than a 5-micron coating of vanadium TCNE magnet on a piece of broken glass, and it adheres to a cobalt samarium magnet. Here it's on Teflon tape, flying through the air. Here it is on aluminum, being attracted to the magnet, and we all know aluminum is not magnetic to do that. So we in fact have a way of making thin film magnetic materials. So let's divert a little bit to the future, and we all know about electronics with electron flow in a copper wire. Very important for society to do that. And now we're shifting gears to high-tech spintronics, where the electron has to be up or down, otherwise it will not move forward in there. And this is a useful information carrier. And we're moving towards magnonics, where the information carrier is the magnon, pure spin flow current, no particle movement. And this, of course, is a spin density fluctuation in a magnetically ordered material that can propagate in spin wave quanta or magnons on surfaces. This is sort of like, at least as a chemist, a wave at a sporting event where going around the stadium, hands go up and down, and this propagates. And it has a variety of advantages over other technologies, It's got low joule heat dissipation, supports faster processing, giga and terahertz, and you can transmit electricity through an insulator. It also has higher fidelity, propagation lengths up to the millimeter scale, and you can tune it with magnetic materials or an external magnet, and it's multiplex with many frequencies per channel. So magnetics is sort of an emerging area, and I'm sure there'll be many talks at this meeting on aspects of it. But the point I want to make today is that the YIG, yttrium iron oxide on gallium oxide is a benchmark magnetic material for low heat diffusion and or Gilbert dampening. It's very difficult to make this material over here because GGG is the only substrate people have successfully deposited the YIG on for magnetic studies, and it's expensive and challenging to make it reproducible. And so we questioned, in fact, whether, in fact, vanadium TCNE might be a magnetic material because it's a room temperature magnet and we can grow it on many substrates. And the bottom line, which is a whole talk unto itself, is that in fact we can generate magnons by ferromagnetic resonance to get coherent magnets and use a spin-Seebeck effect to get non-coherent magnons. We can detect magnons optically by Brown light scattering or electrically by spin pumping with an inverse spin Hall effect, and in that case both coherent and pulsed wave methods to do that. And we get fairly respectable values for Gilbert dampening and spin mixing coefficients, which in fact are comparable to the YIG benchmark material for this material. So we in fact have demonstrated the feasibility for magnetics using vanadium TCNE. This is the team of physicists at Utah that were working together studying this material. Mostly Valerie Vardini's group and Christoph Bohm's group are the ones that have spearheaded the physics effort to make this a successful study. Now back to chemistry. Talked about vanadium and TCNE. I'm going to replace the vanadium with other metals, manganese, iron, cobalt, and nickel. I'll talk only about manganese today. And if you look at chi versus T, there's a little glitch over here suggesting an anti-ferromagnetic coupling, but it does order, as we'll point out, to 69 Kelvin, nowhere near 400 Kelvin. But nonetheless, it's still a respectable value to do that. Now, the structure of this has been determined by powder X-ray diffraction, Rietveld analysis, which is a no tricky method by itself. And it has layers of buckled manganese in purple, surrounded by 4 TCNE radical anions. And the manganese has 5 spins, the TCNE has 1 spin, and it's interconnected by the sigma dimer of TCNE octocyanobutane dianion, which is diamagnetic. So we have this corrugated structure, and there's about 45% of the void spot volume is filled with solvents, and who knows what else is floating around in there to do that. So this is the structure of the material, layers of magnetism interconnected by diamagnetic material to do that. Now, I'm going to look at the data. I just showed you the chi data a moment ago, and I repeated it over here. The cusp over here, indicative of anti-ferromagnetic ordering. The hysteresis loop, or lack of hysteresis loop, no remnant magnetization, no coercive field, and other data we have indicates that in fact it is a bulk 3-dimensional anti-ferromagnet. And we get the TC from the Fisher specific heat data. We can talk about that later if you want. So let's ask how this actually occurs. Each manganese 2 site has got 5 spins, we'll call them up in yellow, and it's connected to a radical anion of TCNE with a spin in the p orbital over here, and that's antiferromagnetically coupled. And each manganese is surrounded by 4 TCNEs, so each of the 4 TCNEs are antiferromagnetically coupled, spin down. And each TCNE is surrounded by 4 manganese with spin up to do that. So all the manganese spins, 5½ are up, all the TCNE spins are 1/2 are down. And now you're looking at a layer, and I'm going to make it edgewise. And when I make it edgewise, it looks like that. And now keep that in mind, and I've given you the entire structure, and here's the coupling that I showed you a moment ago. And this layer over here is antiferromagnetically coupled to nitrogen, carbon, 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 nitrogen, such that all the manganese spins on that side are down, opposing the ones on the next layer. And so we have a ferrimagnetic layer, antiferromagnetically coupled to another ferrimagnetic layer. And that gives you a bulk antiferromagnet. It's the hard way of making a magnet, an antiferromagnet, to do that. And when you think about it globally over here, that in fact it's antiferromagnetic coupling to this non-magnetic layer, it's effectively an artificial or synthetic antiferromagnet. And so let's spend a second on that. The intrinsic artificial or synthetic antiferromagnet basically was described by Berg in 1996 as antiferromagnetic coupling between ferromagnetic layers via a thin non-magnetic layer to form an artificial antiferromagnet. And the importance of this led to GMR, giant magneto-resistant devices, which require this construct in there that's made by atomic deposition. And of course, as you well know, in 2007, Furk and Grunberg received the Nobel Prize for the GMR. But what we've done is made synthetic antiferromagnets from a chemical point of view, multi-layer. We don't need atomic deposition for that. And so our system is coupled together by this non-magnetic layer separated by almost 8.8 angstroms, and that gives you the coupling. It is one of many artificial antiferromagnets that we have discovered, and we're only talking about this one today to do that. And I want to point out that people have hypothesized that such antiferromagnets are more effective at propagating pure spin currents without heating versus dielectric materials, and you can go to terahertz and dynamics for faster. So this is a type of material that could be useful in the future. Now that material I just showed you a moment ago is re-illustrated here, except I also have the field-cooled and zero-field-cooled data, a little glitch over here at about 70 degrees. And now I'm going to put pressure on it. And when I put pressure on it, this data point over here, because this goes from 0 to about 8, this goes from 0 to 1100, so that red point is over here. And as we put pressure on it, we actually can get growth in a ferrimagnetic behavior at higher pressure to do that. And if we look at the phase diagram of it, up to basically over here, about 1.5 kilobars, it's antiferromagnetic, and then it kicks in to be a ferrimagnet whose TC increases linear with temperature reversibly, goes right back to 0 if you reduce the temperature of the material. And so in fact, it's an antiferromagnet up to 0.5 kilobar, ferrimagnet above that, and the magnetization increases up to 3 orders of magnitude in doing that. We don't fully understand the structure of this. It's interesting magnetic material. Now, as a chemist, we play around with all sorts of things. I'm going to stay with the manganese. I'm going to stay with TCNE. I'm going to stay with the iodide that I talked about. I'm going to change the solvent from acetonitrile to THF. There's only 3 THFs per manganese, and that's basically what there was in acetonitrile, but we're doing the same chemistry, and I'm going to show you 2 different infrared spectra. Not important, except they're different. Similar, meaning we expect U4 TCNE radical anion, just like we had a moment ago over here. But if you look at the global structure of the material, you can see chi T versus T plummets around 170 degrees, and the theta value intercept from the Curie law is about 100 degrees higher than the previous compound. So it's completely different material, but still magnetically ordered. Now, to be honest with you, we had no idea what this was. And we took a polycrystalline sample, gave it to Peter Stevens, who did powder X-ray diffraction, refilter analysis, and magically, he got a structure. And the structure has the same corrugated U4 TCNE ferrimagnetic layers. But in between the layers, instead of having the diamagnetic octocyano-butane dianion, it has another TCNE radical anion. And so there's a spin here where there was no spin before, and now it's interconnected to doing this. And now we have 3 halves of a TCNE per manganese, and we need a counterion. I don't know what it is, but the crystallographer figured it out. And the counterion is triiodide, I3 minus. And if you look at it, here's the cage structure of manganese and TCNE giving you the bridge, and ionically in the middle are triiodides in the middle of the unit cell to do this. And I have to give a real chemical equation that's balanced for a change. That's the equation. It's good for freshman chemistry. It's not easy to figure it out. But the key thing here is it now magnetically orders as a ferrimagnet, not an antiferromagnet. And the magnetic ordering temperature determined from the bifurcation of the field-cooled and zero-field cooled as well as the remnant magnetization going to 0, is basically 171 Kelvin, over 100 degrees higher than the previous compound. And here's the hysteresis loops that you expect for a magnetically ordered material that's a ferrimagnet to do that. So let's ask why this occurs. And the answer to that has to do with simple analysis of the spin coupling. Here's the same layer I showed you a few slides ago. All the manganese yellow spins are up, 5 halves. All the TCNE spins, 1 half are down. Couple antiferromagnetically to give you a ferrimagnetic layer. But instead of coupling to the next layer through this diamagnetic one, here's a spin over here. It's a radical anion, ours are these 2. So they have another spin. And that spin couples antiferromagnetically to all its manganese needle. So the entire 3-dimensional bulk material has manganese spin up, TCNE spin down, 5 halves minus 1 half. It orders as a ferrimagnet and doesn't have the coupling through the non-magnetic layer to give you an antiferromagnet. So we fully understand what's going on for this material. Now I want to switch gears and go to another compound to show that these are not flukes. There's some bizarre material. This material is manganese tetraphenyl porphyrin. Manganese, 4 phenyls. Now if you put in iron and different gunk around it, we call it hemoglobin. If you put in magnesium around it and change the organic spinach, we call it chlorophyll. So you're familiar with the red and the green. But this is manganese, and it's simplified with phenyl groups. And it's manganese 2, and you mix it with TCNE. TCNE gets reduced, manganese 2 gets oxidized, so it goes to manganese 3. So there's 4 spins on the manganese, 1 spin on the TCNE, and it forms a chain structure. 4 spins, 1 spin, 4 spins, and these chains are parallel to each other. So a good physicist would call this a one-dimensional material. You open up the book and it says, thou shalt not have magnetic ordering or any cooperative phenomenon in one dimension. Fortunately, this molecule did not read the book, and it magnetically orders with hysteresis 16 Kelvin, depending on what the material is for this material. Now notice at 5 Kelvin, the hysteresis loop shows a coercive field of 375 Ersteds. Nice textbook hysteresis book loop. However, if you cool it down, it goes from 375 to 27,000 Ersteds at 2 Kelvin, reversibly. So at 2 Kelvin, this has a very high coercive field, higher than any commercial magnet you can buy today for this material. So it's a very interesting example of many different forms of this material that we have, and gives you some new physics phenomenon to think about. Keep in mind, of course, that strong magnets are indeed still important. Now, I think this is the last compound I'm going to have you suffer through. This is called ruthenium acetate. And these brown balls over here are a metal site surrounded by acetate, 2 oxygens, a carbon, and some organic fat, in this case methyl, so it's an acetate. Over and each of these oxygens bridge both metals, and we get a pinwheel of D4H symmetry for this material. If these metals are copper, then you think about Linie-Bauer equation, spin coupling in copper 2, and there's no bond between the metals. Nice piece of physics, very important to the evolution of magnetism. If you have ruthenium in there, then in fact, you have a double bond in there, and the electronic structure of this bond is that there are 3 unpaired spins over these 2 ruthenium sites, 2 in perpendicular anti-bonding orbitals of pi symmetry and 1 of anti-bonding delta symmetry in there. Now, as a coordination chemist, a physicist wouldn't appreciate this, but there should be 6 coordinate, and it's 5 coordinate, and there's a vacant site on this side and that side, and we can use that to construct something. So we want to add something to both sides, and we selected chromium hexacyanide. The nitrogen Lewis base that can bind to the rutheniums, right and left, to give you a chain. But chromium hexacyanide has 6 cyanides. So besides right and left, it can go up and down and back and forth and construct a cube. And the charges will balance because you have 3 ruthenium plus 1 dimers per every chromium trianion, perfect charge balance. And you can predict that the chromium-chromium distance in the cube is approximately 13 1/3 angstroms. And we went in the lab and we made this. And in fact, we got perfect elemental analysis and powder diffraction data that tell you it's a cube with a value of 13 1/3 angstroms. We designed it, it came, but there was a little surprise, and I'm sure someone in the audience has picked up, that's not the powder pattern of primitive cubic atom, that's a powder pattern for a, of a body-centered cube, not a primitive, which means effectively this is the structure of a primitive lattice. And to make it body-centered, we have to put another chromium in the center of the unit cell, and that chromium has the identical lattice as the red lattice, colored blue, to show there are 2 interpenetrating lattices that have no chemical communication through bonding between each other. If you're an ant walking on the blue lattice, you'll never get to the red lattice. They're just not communicating that way to do that. And of course, we've solved the structure of a powder diffraction. We verified the density. It has got this structure. And it's a ferrimagnet, an unusual ferrimagnet that orders at 33 Kelvin. And I just want to show you there is no bifurcation of zero field cooled and field cooled data, which is unusual. And the hysteresis loops, I call them mysteresis loops because of the mysterious nature for these materials, but has this kink in it reproducibly over here, constricted shape. And if you put pressure on it, TC goes from 33 Kelvin, increases at a rate of 2.1 Kelvin per kilobar applied pressure linearly and reversibly for these samples. So it goes up to about 60 Kelvin if you're under pressure, at least at room temperature, to do up to the pressure limit we had to do that. But more interesting, the hysteresis loop in red with the constricted nature becomes normal shaped after you do that, and if we remove the pressure, back to the funny shape. So it's a very interesting compound. Well, to summarize, our group has made over 12 families of organic-based magnetic materials. The ones we talked about today are decamethylferrocene TCNE, manganese tetraphenyl porphyrin TCNE, 2 TCNEs per vanadium over there, manganese with 1 TCNE, well, 2 TCNEs, the other one being half of its dimer over here. Manganese TCNE, 3 halves, iodide, 1 half over there. Talked about the ruthenium acetate. We've made lots of other materials. Many others have room temperature or higher order room temperatures and other things. I just wanted to give you a flavor of different chemical compositions and structures and different magnetic properties to show you that organic-based magnets exist in there. And to summarize that, yes, you can make organic-based magnets. I want to point out that you can make ferromagnets, ferrimagnets, metamagnets, antiferromagnets, artificial antiferromagnets, weak ferromagnets, which are also canted antiferromagnets, spin glasses, we see magnons, carbon magnets. I know we can talk later here, one of my friends give a talk, photomagnets, ordering temperatures well above 100 degrees centigrade, controllable, high-low saturation magnetizations, high-low coercive fields, demonstrated a variety of applications in our own lab. Other people have made other important contributions to doing that. And worldwide, people have been studying these materials. There's lots of representation from Japan here with very important and interesting compounds that you'll hear about later in the talk today to do that. And I want to give you an indication that there's lots of opportunities for both chemists and physicists for synthesis, modeling, computational studies, experimental studies, exotic ones, and theories. We always need some new theories. Now I'm going to show this cartoon over here. This cartoon actually was published in 1916 by the president of the Royal Society of Chemistry, anticipating the structure of some compound whose structure wasn't determined for another decade after that. It's whimsical, it's comical, but I put spins on it just so you can have cooperation of spins. But to be honest with you, the real take-home message is spins are important, cooperation is important, but the most important cooperation is people. Physicists working with chemists, metallurgical scientists working with biologists, all the important problems in the world of society today, air pollution, medical issues, we have to interact and cooperate, work with other people, learn their language, learn the other people's language, work together, cooperate, and interact, and progress will be made in many areas very quickly with that philosophy in mind. Now, I sort of hinted, a little bit earlier about the history of magnetism, and told you it was found in China, and then there was some stuff about a shepherd walking around this area having nails and rocks adhering to it. I like to believe, and I'm not a historian, that the discoverer of magnets were in fact cave kids. They're playing around in their cave, and they're inquisitive, they're curious. And someone asks an important question. Oops, I did something wrong here. Basically, why are these rocks different than all other rocks? Because they stick together. And this is the types of discovery alluded to at the very end of the last talk of not predictable stuff, paradigm shifting, new discoveries completely, and particularly from the younger, which was 99% of you, than I am. Think about, does this make sense? What's causing this? Maybe that's the opening to some really new science to do that. And I'd like to believe that magnetism has come a long way to include organic-based materials. They're not so nice looking. They're called designer magnets. But I'd like to believe magnetism and superconductivity and quantum mechanics have a bright future to do that. I'm just going to throw up names of people who have been in my group over here over the years. Ming is, I have to highlight Ming because he showed up at this meeting. I was happy to see him to do that. And we collaborate with a physics group in Ohio State. Art passed away about 4 years ago, but we did many things together with that group over there and collaborate with people worldwide for many exotic experiments. For the younger folks, challenges for you. Make transparent insulating magnets. No one's ever done that before. A flexible magnet. A photomagnet. Very hard, high coercivity magnets. We've given you some examples here. Very soft, high permeability magnets. Can you make a liquid magnet? Can you make spintronic, magnetic, spin transistor materials, and all organic motor? These are opportunities for you in the future to do that. And remember, the Earth is a magnet. Come and visit us in Utah. And this is what it looks like when you jump out of an airplane over Salt Lake City, and make sure you land over there, because that's the football stadium where they had the 2002 Winter Olympics. And my office is about 90-second walk from there to do that. And just to give you a view from our house, we're about 1,300 meters. Our house is 1,700 meters. And this last year, 23 meters of snow. So it's a good place to ski. And thank you for the invitation again and your very kind attention. And I'll try to answer any questions that I can do. Thank you very much.
Thank you for such a nice talk. Are there any questions or comments?
So I'm a physicist.
Good for you.
And
my best friends.
And I have to value what Phil Anderson says. In the first part of your talk, I got the impression you were going to tell us about organic materials that are ferromagnets, etc. But everything you showed has iron, manganese, something in there that's not organic. And I'm just wondering if the ultimate goal is to get rid of those and have an actual magnet without any 3D and
we've made lithium TCNE. Would you argue lithium is like iron?
No.
Good. It magnetically orders too. Fairly high, not as high as these, but it does magnetically order as a weak ferromagnet. So it's not essential. They contribute those spins, yes, that's true. But you can make, and Kinoshita has made in Japan, purely organic materials. Katsui was involved in many of these studies as well as other people. Yeah, there are many examples. The TCs are much lower. The first purely organic one hit 0.6 Kelvin. And that's not what we were studying, but they're legitimate to do that. So it's a question of what you want as a goal. And I think the flexibility of designing them to fabricate them and to have different properties, which comes with the organic chemistry, which ancillary has spins and p orbitals, and the metals are there, but they're really more organic-like than iron metal or iron oxide or classical things. So we can quibble about that, but in the examples like decamethylferrocene, TCNE I showed you, and these other ones, I can put other closed shell related cyanocarbons in there, and they won't magnetically order. The spins in the p orbitals play a big role, which is the new novel feature to do that.
So it's those small spins in the bridging layers, the TCNE or whatever.
Yeah, the TCNE has one spin over all 10 atoms. And I
just want to clarify, that's what's really significant.
And that spin directly couples, not indirectly by spin polarization, but directly couples to the spin on the manganese or iron or whatever in that case. And the decamethylferrocene it doesn't, because there's no bond between it. It's ionic to do that, which itself is interesting to do that. Yeah. Does that help you?
Yep.
I'm here for a while, so more questions come up. That's great.
Another question or comment? Thank you for showing us all this beautiful data. I wanted to follow up on the comment of organic molecules that don't read physics books. So there were two examples, one of what Phil said. Was there part of the argument that was missing there? Was it the spin on the p orbitals that makes the difference between that discrepancy? And number two, about the one-dimensional structure where magnetism is seen. Is there some canting going on in that molecule, or did we really get one-dimensional magnetism wrong?
Well, I mean, if you believe it's truly one-dimensional, then it should order, and it is order, and nothing's really one-dimensional. There's some coupling between them, and arbitrarily it's much weaker, but not zero. So the answer is, yeah, there's something's got to be going on in those systems to do that. But if you go back to the very first example, excuse me, decamethylferrocene, TCNE, there's no bonding in the chain or between the chains, so it's all through space interactions, and still magnetically orders. I once was given a complaint at a meeting. Someone gave me a talk, why is that low, 4.8 Kelvin? And I couldn't answer that because the physicist got up and jumped and said, you're asking the wrong question. You should ask why it's so high, the ordering temperature. So.
And for Phil Anderson?
No, it wasn't Phil Anderson.
No, in the beginning part of your talk, you said that it was improbable to have, according to Anderson, this
Well, he didn't use that word, he used lots of other words, which meant it was not going to happen.
Okay, so was there something missing in his argument that you found? Was it the spin?
No, I think it was an opinion.
Just an opinion.
He didn't write many.
He had many opinions.
Yeah, but sometimes he had equations to back them up. This one was just an opinion. There's two more here.
Here on the room. Here. One here first. First here. Thank you.
Thank you. Yeah, very nice talk. You covered so many things in magnetism and in results organic materials, but I think one thing which was missing all this like chiral materials, let's say something like magnets with Teleshinsky-Mori interaction.
Katsui will talk about chiral magnetic.
Okay, but can you just maybe like very briefly say something? So, like, is any issue to have some spirals, magnetic spirals and so on? Or?
Why don't you answer?
Okay, maybe I'll wait until you talk.
The answer is it's achievable.
Okay.
Wait for him, the expert in that.
And they conducting, right?
No, they're not conducting.
Oh, they're not conducting.
Yes, another question?
Thank you.
Professor.
It's just some people will say it's a semantic question, but I think it's an academic one. It's the question about organic or inorganic. And there are now a certain tendency to say molecular and non-molecular. An example that we give when we teach inorganic chemistry is that if you compare sodium chloride with carbon tetrachloride. They are two inorganic compounds. But if you compare methane with carbon tetrachloride, then they are two molecules which are identical. So in fact, the difference is not whether it's organic and came from a tree or an animal, or whether it's molecular or not. So the tendency is to distinguish chemistry in two big branches. Organic and inorganic was the past, molecular and non-molecular is now. But I'm sure I say that I'm a professor of inorganic chemistry, so even if we talk about this, the general idea that people have is that organic and inorganic. But molecular and non-molecular is a little more precise. That's what
Well, the other feature I want to point out is where the spin is, the p orbital versus d orbital or f orbital.
Yeah.
That's another way to do it.
That's a nuance which is important, of course.
Any other question or comment? Back there.
Organometallic chemistry has been merging those areas for a while.
Yeah. Thank you very much for your very informative and interesting talk. I have just one question. You showed several times zero field cooling and field cooling curves. Usually this phenomena is associated with presence of magnetic particles or small magnetic grains in non-magnetic matrix. And even from these dependencies you can evaluate block in temperatures, etc., etc. Is there any sense to apply this methodology in your case, or what do you think?
We've not studied the granular or the information based on that at all. But it's well taken. The point is we do take it down to low temperature, and we can bring it down in our instrument down to about 1 milli Gauss, and then we can do zero field cool, and then we can do those experiments. But we've never studied that as a function of crystallized size or anything like that. So I can't answer your question.
Okay. I just was thinking about magnetic and homogeneity.
Yeah.
Okay. Are we missing any questions?
We've taken crystals, by the way, some of them, and put them in a magnetic field, and they all line up like that. So we can do that in some cases.
There seems to be no more questions or comments, but I have one for you. Here. You cannot see me. Here.
Oh, there, okay. You are hidden in plain sight.
Yes, exactly. Yeah. This is how science works.
Yeah.
You have everything right in front of you, but you cannot see it.
That's right. And then some 4-year-old kid tells you what's
So, since you're talking about molecular, can this is polycrystalline?
Many of them are polycrystalline. A few are done by single crystal magnetization, and many were studied by single crystal diffraction. But general experiments we've done are on polycrystalline samples.
So the question is, of course, whether they're polycrystalline or single crystalline, they have gone through a solidification or some crystallization in some way.
Crystallization.
And then there is an intermolecular and an intramolecular space. How important are they to determine the magnetic properties and the stability of these systems?
Well, the answer is they're obviously important because you have to worry about the connectivity of atoms and versus the through space this way. And generally, the through space are weaker, but nonetheless they're significant to give you coupling, to give you three-dimensionality, to give you the magnetic ordering to doing that. But the first compound I gave you was totally ionic, and then I had chain compounds which had weak interchain interactions, and layered compounds that had weak interlayer interactions, and then some with more significant ones. So everyone's different, and you have to try to analyze them. Not always so trivial to do that.
Thank you. So if there's no any other questions or comments, then we'd like to thank you and all the speakers for their excellent talk. Now we have 1 moment because we have to give the diploma, which is very important. And also remind you again that